A Star Trek engineering uniform. I guess I'll have to watch Star Trek to understand. I know, you guys all have your fancy backgrounds. All right, so let's see here. First, let's talk about some Webassign issues. So definitely with 2.4, been having some crashing issues. I did just delete one of the questions there, so maybe that helps. I guess there was just the one question that kept crashing, but looking at the scores, someone had managed to do it. So I don't know. I sent an email off to Webassign earlier today to see what's going on, but I haven't heard back. So, which kind of blows, because our old Webassign person, she was so good, she was so fast, and then this guy is just kind of a dud. So there, I said it on YouTube. Hopefully he's not sifting through hours and hours of video for a mention. Okay, so let's see here. So what I'm gonna do, so if you're having trouble with Webassign, so if it's crashing or anything like that, then just send me a text right away, and I'll kind of see what I can do, or try to figure it out. He's a Webassign coach. He cries every day. Probably. Probably. And he's probably sick of all my questions. So that doesn't help. All right. What was I saying? So if you have any technical issues with Webassign, text me right away. I know, that wasn't very nice. We're anti-bullying, and I'm the bully. I know. I'm sure he makes fun of me too, though. So, text me, so 250-864-8386. Text me right away. Right, so if it's crashing or whatever, yeah. Well, I mean, you do get the ebook, but not an actual textbook. But yeah. So just text me, and then you don't have to kind of work through that on your own. It's always a good idea to contact support, but I suspect, it sounds like, Reid, you've had a couple of run-ins with support already. Sounds like they were not solving the issue, just kind of resetting you. But anyways, so we'll see. But like I said, I can, delete questions if you're finding that one is giving you grief or whatever. So I did delete one of the questions from 2.4. Hopefully that makes it run smooth. I don't know. Who knows? Okay. All right. Any other admin stuff? Michael's jamming out. It's good. I think that was it. what I can do, I can extend the due date, but I'm kind of waiting to hear back on the Webassign. But if it's not letting you even enter the assignment, then just let me know. Hey, the Tiger King is with us. And a little Shiba Inu. All right. Let's see here. Oh yeah. Let's get started. So all right. Review, but honestly, I don't know. We talked about permutations and factorial. Permutations, we'll re-emphasize it, right? But that's when order matters. And we talked about factorial, which is the exclamation mark. Right? And then we started talking about distinguishable permutations. So we said, okay, well, where were we? So this is from last day. So if we have indistinguishable elements, right? So we've been assuming so far that we only have, you know, so many letters to choose from, and they're all distinct and they're all unique, right? But if we have indistinguishable elements, but order matters, right? Then we went through a quick example, which we'll pick up on again. But if we have a word like assist with 3 S's, then we have 3 indistinguishable elements. So how we're going to go through and deal with that and find the number of unique permutations is you think of all the letters as being unique. So distinguishable from each other. And so you find how many unique permutations you can get. And then you take all your indistinguishable letters, let's say, or numbers or whatever you're dealing with, and find how many unique permutations of those you can get and divide those out from the total. Okay. So we had assist, so we've got 6 unique letters, and so if you're trying to rearrange into a 6-letter word, a different 6-letter word, then you've got 6 permutations where out of 6, or just 6 factorial. So 6 factorial is 720 ways that you can rearrange the words in assist to make 6-letter words. Distinct letters are non-repeating letters in the word. Yeah, exactly. So A is distinct and distinguishable. I is distinct and distinguishable. T is distinguishable, but the S is not. Cool. So then we take all our 3 S's, right? Because we have 3 S's, so they're indistinguishable. We could have S1, S2, S3, S2, S1, S3, S3, S1, S2, and they're all just SSS, right? And so we divide those out. So we get 3 factorial, which is 6 permutations. So unique permutations, we have 120 unique permutations of 6-letter words in the word assist. Okay. Now let's go back here, because we've actually just got a formula for it if you want to. I think it's actually okay to just go through and divide out the number of non-unique elements, but the formula helps if there are multiple indistinguishable elements. And so multiple categories of indistinguishable elements. So if we've got the formula, oops, for distinguishable permutations, distinguishable permutations. Of course, there's a little blurb. So the number of distinguishable permutations of n objects of which n subscript 1 are of one kind, n subscript 2, oh, that looked like a 2, are of another kind, and n subscript k are of a further kind, well, I guess I should say so that n is a sum of all these things, right? N1 could have just one element, right? N2 could have 4 elements, right? But N1 plus N2 plus N3 plus all the way up to plus Nk has to equal N. Okay. So the number of distinguishable permutations is denoted by and if you've seen this choose function before, it's a little bit different, so kind of don't get thrown off, but it'll be different in the sense that it has multiple things in the bottom. So we've got n up top, so we're going to have 2 round brackets, so, and it's going to span essentially 2 lines. And so n up top, and then n1, n2, n3, nk down at the bottom. So this becomes, just by definition, n factorial over n1 factorial, n2 factorial, n3 factorial, all the way up to nk factorial. Which is essentially what we were doing, right? We took, what was it? 6 factorial, and then we divided by 3 factorial, which, because there was only one a, right? So n1 would be for the a, which would be 1 factorial. 1 factorial is just 1. And then there's only one I, there's only one t, right? So it ends up being the same thing, which we'll show. So for example, this is a definition, so I'm just going to put a pink box around here. Haha, made it too big. Hey.
Sorry to interrupt.
Right.
Is there supposed to be a divide line in the brackets there?
No, so it's just kind of weird notation. And we'll see it again in the choose function in the combinations in the next section. But there's no divisor in there. Typically we read it as n choose something. So n on the top and then choose whatever is on the bottom. But in this case, it's a little bit unique. this one's good to know that it exists. I feel like I've done a lot of kind of combinatorics work, and this one doesn't really come up that often, so don't worry about it too much. But it's good to know that it exists, because there are other ways that we can do it. But so, like, for example, if we have the word assist, right here, we've got n is 1, 2, 3, 4, 5, 6. If we have n1 representing the A's, let's say, there's one A. Right? So n1 is 1. There's one A. If we have n2 representing the S's, there are 3 S's. Maybe I'll put this on the next page so it's all on one page when we're done. So I typically just move through whatever letters I need to move through and just pick out distinguishable elements. So my next one is going to be N3, which is the I, and then just so I can have the blue pen for a little bit longer, my N4 is for T. What are we trying to achieve with the word assist? We're just trying to create 6-letter words. So different 6-letter words. Does that help? So
not actual words, like just how many combinations that can make?
Yeah, so letter combinations of length 6.
Oh, okay, thank you.
Cool. Good. Yeah, so basically how many scrambles can we get? N3 is for the I's, so the number of I's, there's only 1. And then for the number of T's, there's only 1 as well. So then, I'll summarize it here. The number of letter arrangements of length 6, we can get and we denote it by 6 is the total number of letters. And then we've got 1, 3, 1, 1, all in these big brackets. No fraction here until we calculate it, right? That's going to be 6 factorial over 1 factorial, 3 factorial, 1 factorial, 1 factorial. You can drop the 1 factorials and then just be back to where we landed on last day. So this, if you don't have your calculator, I mean, you should have a calculator for this stuff because some of the numbers get really large. But if we do 6 factorial on here is 720 divided by 3 factorial, which is 6. Oops. We're back to 120. Same solution we found last day. Oh yeah, any sort of, since you're just working on your own, any sort of calculator, so Google works fine, right? Your phone, even though your phone's kind of annoying, or at least I find it annoying. Yeah, you can have any sort of calculator. Okay, good. Nice. Let's do the same thing, but with more than one group of indistinguishable elements, right? So, for example, find the number of distinguishable permutations of the letters in the words, and they just use the name of the textbook, so that works fine with me. Nature of mathematics. So I need to count how many letters in total, right? Oh yeah, Michael giving it away. And then what if we include spaces? So let's exclude spaces for now, right? So we're not counting spaces. I know, spoiler alert. So let's not include spaces first, and then we'll change it by including spaces. But things you need to think about, right? That's good. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 letters. So N is 19 letters, not including spaces. So this is totally random, but have you guys read A Short Stay in Hell? Anyone? It's just like a short novel, I guess. Can't say I have. Well, it's a quick read and it's actually really interesting. So the idea is you go to hell, but you have to go through all the books. So they've got all these different permutations of all these different 300-page books or something, and you have to find the story of your life, and you're just constantly searching through all these books, and you can't even find words, let alone full sentences. But anyway, so very side note, but it's what this stuff makes me think about is, okay, so you've got different permutations. Some of them make words, right? Like we talked about. Most of them are just going to make gibberish. So, okay. So there's 19 letters, right? And if we just kind of go through and say, okay, well, instead of using N1, N2, N3, yeah, you can quote me on that. Yeah, a little fun story. Instead of using N1, N2, N3, I'm just going to use the letters themselves. I think it's a little bit cleaner. And there's really no harm in doing that. So what I'm going to do is I'm going to have n, I've got 1n in total, right? So now I'm just going to go through and see how many unique categories I have and how many elements in each of those unique categories. So I've got 1n, I've got 3 A's, I've got 3 T's, nature, count my U's next, I've got just 1 U, so I usually just work my way through until I've caught them all. Gotta catch them all. So I've got 1 R, I've got 2 E's, that's nice. As someone with now 5 E's in my name, that's pretty good. How many distinguishable permutations? Not very many. O, there's only 1. F, there's only 1. M, there are 2. H, 1. I, 1. C, 1. S, 1. Hey. So all these 1s, 1 factorial is just 1. So we don't really need to write them out, right? You can just ignore them if you want to. But what we have is the number of distinguishable permutations is going to be 19 factorial, right? How many we had? And then, because I don't want to skip too much, I'll do my 3 factorial, 3 factorial. As I go, maybe I'll put a little check mark here just to make sure that I've done it. And then moving down to my 2 factorial, 2 factorial, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 1 factorials. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Required a lot of concentration actually. 1, 2, 3, 4, 5, 6, 7, 8, 9. Hey, what do I care? They're all going to go to 1 anyways. No, they don't matter. I'm just putting them in for completeness. So this here equals 1, so can ignore them. So then we get, well, you can use your calculator. You can, yeah, I'd probably use my calculator because remember that one trick that I showed you the other day where you could go list out 19 factorial until you find the largest value to cancel it with in the denominator. In this case, the largest value is 3, so you'd have to list a lot and do a lot. So I'm going to have 19 factorial is huge, divided by 3 factorial is still huge, divided by 3 factorial, divided by 2 factorial. What am I doing? Divided by 2. Why did I say that? 2 factorial is just 2. That's easier. So here, this becomes 8.4475 7, 6, oops, 5, 7, 6, 4, 1, 7 times 10 to the 14. Assuming you guys are good with scientific notation. Cool. Because it's huge. Can't do the bottom ones in brackets. Do you mean the 3 factorial, 3 factorial? So you don't do them? Yeah, you do. But because it's just multiplication and division, you can go through and do them individually. Because it's like shoving the 3 factorial up and then 3 factorial and 2 factorial, 2 factorial. But yeah, you would do them in brackets and then divide them out. Good. Good, good, good. So what if we consider spaces as well? What if we consider spaces as well, right? We can do it, but oh. Wolfram Alpha notes that this number is about 42 times the number of red blood cells in the human body. That's pretty cool. It's huge. 42 times a lot. It's a lot. Okay, so now n is going to be 19 plus 2 spaces, right? We've got nature, space, of, space, mathematics. So now we're considering characters, right, which includes the spaces. Two spaces which are indistinguishable. So now we would have 21 factorial over, and now I'm going to drop those ones just because I'm lazy. 3 factorial, 3 factorial, 2 factorial, 2 factorial, 2 factorial. And these ones are from the 2 spaces. Any questions about that one? Okay. Should we do 12.2? Why not? 12.2 is on combinations. For me, combinations are, I don't know, I've always liked combinations better, mostly because the order doesn't matter, right? So it's just, hey, how many ways can I pick 4 things out of 10, right? And so order doesn't matter anymore, right? I'm not picking the first thing, picking the second thing, picking the third thing. It's just a set now, right? We're, again, in a set, order doesn't matter, right? So if you think about combinations, you can kind of mix things around, okay? Calculations, I think are a little bit easier to wrap your head around, and so there's not a lot going on. And just as a heads up, in 12.3, there's not really new material. We're just gonna go through and read different scenarios from permutations and combinations and figure out which ones to use, or maybe a combination of the two. Right, and so it's just going to be kind of exercises in there, so don't worry. This is kind of the end of it. So remember, if we're choosing elements without repetition, so that's going to be a key thing that we'll come back to touch on, right? What do we do if we have repetition, right? But if we have no repetition, then a permutation is where order matters, right? And a combination is where order doesn't matter. So when choosing elements without repetition, a permutation is when order is important. Okay. So I think we talked about, okay, so you have to elect a president, and then you elect a secretary, a treasurer, right, in order of prestige, I guess. And so here, elect a president, oops. Elect a president, then a secretary, etc. Whereas a combination is you're just gonna elect two people to a group, right? And so to some sort of, they call it the committee problem, but any sort of kind of lump where you're all on the same level and doesn't matter what order you came into that group in. So a combination is when order is not important. Elect two people. So that's a summary of what's going on here. So a combination is a little bit more relaxed, is how I kind of remember it. So by definition, combination, so a combination of R elements of a finite set S of n elements is a subset. We've talked about subsets, right? So is a subset of S that contains R distinct elements. That contains R distinct elements. Put a little box around here. So we've got two different notations for the same thing. So for combinations, On your calculator, you've got probably an NCR button. Definitely Google does. So here it would look something like, I cannot see, but anyways, I tried. But usually we use the notations. The notations NR, so we've got those round brackets again with no line in between. And I really have to hold back because I just automatically do a fraction, but it's not a fraction, it's round brackets, so it's the N choose R. So we read this as N choose R. And just like we used NPR, we're going to use N capital CR. So subscript N, capital C, subscript R are both used to denote the number of combinations of R elements selected from a set of N elements, right? So a subset of size R or cardinality R from a set of cardinality N. So are both used to denote the number of combinations of R elements selected from a set of N elements. Elements. Of course, you wouldn't try to pick 5 from a set of 3, right? So especially if without repetition. So we'll just say that R must be less than or equal to N. You wouldn't try to do that, but that's what a lot of these assumptions are about. Saying things you wouldn't try to do. So N choose R, right? I'm gonna, usually I'll use this, the N choose R notation, even though you would read the NCR the same way. Mostly because in future math, if you have to do any future math, which I think you do, right? You have to take, shoot, what's that one called? 251. Can't remember what it's called, but anyways. So there is math in your future, and usually we would use this notation. So that's the one that we should kind of get in the habit of using. N choose R is by definition N factorial over R factorial times N minus R factorial. So maybe I'll put a little box around that, because that's good to know. Okay. How about we try to evaluate 10 choose 3. I don't need to take up a whole 2 lines, but it just makes it look easier. So 10 choose 3 using this notation, right? We're going to have 10 as our n, so 10 factorial over 3 factorial times 10 minus 3 factorial. So 10 factorial, just simplifying this a little bit, over 3 factorial times 7 factorial. So here we get to use that trick that we introduced last day, right, with the factorials. So I'm going to rewrite 10 factorial as 10 times 9 times 8 times 7 factorial. And then I'm able to cancel out the 7 factorials and just deal with kind of easier numbers. So this becomes 10 times 9 times 8 times 7 factorial, and I can do that, over 3 factorial times 7 factorial. But these guys can cancel because I'm just multiplying all throughout here, so I'm allowed to do that. So now I have 10 times 9 times 8, which my calculator can definitely handle, is 720. Oops. $720 divided by 3 times 2 times 1 is 6. Yeah, I think it's 120. 720 divided by 6. 120. Again. Okay. How about if you do m minus 1, choose 2? I'll give you guys a quick little moment to try that one out. You can do it Okay. So even if you're still kind of working on it, let's start by just applying the definition, right? So we have n factorial over r factorial n minus r factorial, right? So n is going to be replaced by m minus 1. Right? And you can use brackets just if that helps. So m minus 1 factorial over 2 factorial times n is now being replaced by m minus 1. N minus r, r is 2 factorial. So from here, I've got m minus 1 factorial over 2 factorial. I'll leave it as factorial, even though it's just 2 times 1, so I could just write 2 if I wanted to. Times m minus 1 minus 2 puts me at m minus 3 factorial, right? And that's going to be kind of the key to success here, because now, just kind of by the same process that we have been doing, I can write out that numerator because we're just decreasing by 1 every time, right? So even though we don't know what m is, we have m minus 1 times m minus 1 minus 1, which is m minus 2, times m minus 3 factorial. Okay? So same trick that we were using, just a little bit harder to get to because of that variable. 2 factorial times m minus 3 factorial. These guys cancel. And because I don't know what m is, my final answer is just going to be m minus 1 times m minus 2 divided by 2 factorial, but 2 factorial is just 2, so I can just skip straight to 2. So I get m minus 1 times m minus 2 over 2.
How come you can break down m minus 3 factorial into m minus 1, m minus 2, m minus 3 factorial?
Just because of how the factorial works, right? And so if we have, so let's just, n factorial is by definition n times n minus 1 times n minus 2 times n minus 3 all the way up to 3 times 2 times 1. So we're always just decreasing by 1 whole number every time. In fact, we can only take factorials of whole numbers, so we're safe there. But yeah, so m minus 1 factorial, it doesn't matter, but I would just go from m minus 1 to m minus 2, m minus 3, all the way up to, or down to times 3 times 2 times 1, and then I'm done. Does that make sense?
Yeah, so you just would go as far as you could to make it easier to do the division.
Exactly. Yeah. So same idea. You're going to go, so just like we went and we wrote out 10 factorial, I looked down here at the bottom and I saw that my largest factorial down here is 7 factorial. So what I do is I rewrite 10 factorial as 10 times 9 times 8 times 7 factorial. Because the 7 factorial is just a placeholder for the rest of them, right? 7 times 6 times 5 times 4 times 3 times 2 times 1. But I've got 7 factorial here that I'm able to cancel out. So then by the same reasoning, I'm writing out m minus 1 factorial until I reach the largest factorial in the denominator, and then I can cancel them.
Is that m minus 1 times m minus 2 the final answer?
Yeah, divided by 2.
Is there a reason we wouldn't like multiply out the minus 1 minus 2 and then just, because that would just leave you with, well, I guess that would mean it was nothing.
You could expand it, but I'm lazy, so I won't. Especially because we don't know what m is anyway, so.
Okay.
Yeah. Yeah, you could just probably leave it factor, especially because the question gave you in terms of m minus 1. So it might be nice to stay in terms of m minus 1. Yeah, you could expand it, but same answer. But more work, and I'm lazy, so no thanks. Okay. Good. Nice. How about, I'll make a little bit of room here. Because I think I can squeeze it in on this page. In how many ways can we select a 3-person committee out of 5 people? Right, so we've got those same, the crew of 5 people. Here's my memory exercise. Alfie, Bert, Calvin, Doug, Ernie. Right, and we're just gonna select a committee of 3 people. Doesn't matter, so it doesn't matter if you were chosen first into the committee or third into the committee. If you're on the committee, you're on the committee and you're in that group. And so this is one of those scenarios where the order does not matter, right? And so it's a combination. In how many ways can we select a 3-person committee? Whoops. Out of 5 people. Should be 10. So if we do 5 choose 3, and maybe this is why I like combinations better than permutations, is because the language comes easier, I find. So out of 5 people, I want to choose 3 of them to be on the committee. So it's 5 choose 3 is going to be 5 factorial over 3 factorial times 5 minus 2 factorial. I skipped ahead. 5 minus 3 factorial, which is going to be 5 times 4 times 3 factorial. I'm trying to keep it on one page here, but it's getting crammed. Here's my page break. Over 3 factorial, so those are going to cancel, and then 2 factorial, 3 factorial, 3 factorial, 5 times 4 is 20 divided by 2, putting me at 10. Squeezed in. So let's see here. Oh yeah, so if you did permutations, right? So if you had distinct permutations, so someone is being voted to vice president, president, vice president, secretary, or something like that, then you would have 5p3, which is the 60. Good. Okay. For a lot of these questions, we have to brush up on your deck of cards knowledge, not house of cards, deck of cards. Although Oh, if I was quicker on the draw, I should have some House of Cards trivia for you guys too. First trivia. Why did the last season suck so bad? Unbelievable. If we're talking about a deck of cards, just to outline things that you probably know, but that we need to have put all our cards on the table, so to speak. So a deck of cards, yikes, has a total of 52 cards. Yeah. Oh, Kevin Spacey. No jokers. Yeah, no jokers in this deck. In fact, I don't think, yeah, just like a standard deck of cards for math purposes. No jokers involved. Boring. But what we have is we have different suits. Oh, maybe I should write that up top. Hearts, diamonds, spades, and clubs, which I typically mix up. Doesn't matter. Well, sometimes it matters. And the count of each is 13, 13, 13, and 13. Of course, there's 3 face cards in each of these. Each with 3 face cards. Right, some questions involve face cards versus other cards. I mean, there's so many ways that you can cut a deck. So we can also talk about the color. Well, for hearts and for diamonds, it's red, right? And so gotta work on my big right-hand curly bracket, right? Or there's 2 black suits, the spades and the clubs. And of course, there's 26 of those as well. Those are kind of the more important, green and blue for all you really wild. And also there are more ways to arrange a deck of cards than there are atoms on Earth. Is that true? Well, if McGill University says so, then exactly. We'll just take their word for it. That's good. So another thing that's not, I don't know, it's not obvious to me is that a flush is 5 cards of the same suit, right? So that might come up, but a flush, 5 cards of the same suit. So we used to shuffle a deck in the order of 10 to the 67th. Hey, crazy. Wow. And the atoms on Earth, 10 to the 50. Pretty cool. Just from a little deck of cards. Yeah. Don't go counting atoms. So if you're pulling a deck of, or pulling from a deck of cards, right? Typically we're saying without replacement, right? You could alter it and say with replacement, but because what we're talking about with permutations and combinations hinges on no repetition, so no replacement. So that's the first thing that we have to keep in mind and kind of check. But that's pretty standard. So let's say you're playing some game of cards and you're dealing cards. People aren't going to put their cards back in to be redealt. This is the dealing that never ends, right? And so once it's dealt, it's out there, right? And so it doesn't matter if you get dealt a king as your first card or your third card or your fifth card. If you have a king in your hand, that's what matters, right? And so order here is not going to matter, okay? So a lot of the time when you're talking about cards and counting cards, then the order doesn't matter, so we're talking about combinations. Okay? So, for example, how many kind of standard 5-card hands can we make? So how many 5-card hands exist? And remember, we've got 52 cards in total. I don't even know if I think. Yeah. So if we do this, right? So like I said, order doesn't matter. How I received these 5 cards or the order that I received these 5 cards in doesn't matter, right? What I care about is what I'm holding at the end when all the cards are dealt, right? And so what I'm talking about is a combination. And so it's 52, choose 5. Nice. Okay. Which is going to be 52. Nice. 52 factorial, just for a little bit more factorial practice, 52 factorial over 5 factorial over 52 minus 5, let's skip ahead a little bit, 47 factorial. Only 2.5 million, 2.6. So we've got 52 times 51 times 50 times 49 times 48 times 47 factorial. So that one got a little bit tedious. I'll probably just resort to using my calculator, right, and not do these by hand calculations, but it's good practice. Over 5 factorial, 47 factorial. These guys are going to cancel. Bing, bing. Right? Or 52, choose 5 on your calculator. Puts you at 2,598,960. Oops. 5-card hands. So then, if you take it one step further, we're not going to go into probabilities, right? But if you're thinking about probabilities, right? If you're dealing in a 5-card hand situation, then these are the total number of possibilities that you have, right? And then you're going to be talking about some subset of those divided by this 2.6-ish million, right? So this would be your total number of possibilities, right? And then you're of course interested in specific. There are some really terrible hands, right? And then some better hands that you might be more interested in. So how many ways can we draw a heart flush? How many ways can we draw a heart flush? So remember, there are 13 hearts and a flush is 5 cards of the same suit. Okay. So now I can only draw from these 13 hearts, right? And I need all 5 of them to be hearts. So I'm doing 13 choose 5. 13 choose 5. And I'm just going to use my calculator here. 13 choose 5 is only 1,287. So now you could talk about the probability of a heart flush in total, right, is the 1,287 divided by 2,598,960. Probably very small. 2,598,960. Oh, I didn't do the division. Yeah, please stay on the line. I get 4.95 times 10 to the negative 4. Seems pretty reasonable. It's a probability, so it's going to be small. Okay. So we're not talking about probabilities, but that's where it's used a lot, right? So good. How many possible flush hands can we get? So remember, a flush is when you just have 5 cards of the same suit. If there are 4 different suits, right, we found the probability, or sorry, not, I'm so used to talking probabilities. We found the number of heart flushes that we can have, right? And so now each of those can have a flush, each of these suits can have a flush. And so how many possible flush hands? Okay. You will all be expert poker players, but don't bet any real money, okay? Need a little bit more combinatorics for that. But yes. So how many possible flush hands? Well, now we kind of get out of just it either being a permutation or a combination. Now we've got 4 different options for the suits, right? Oh. Carson's gonna go back and get his tuition back. That's good. You're welcome. Oh, the Wikipedia is 10 less because it excludes the royal flush and the straight flush. Fancy, fancy, fancy. We're just going overall flush. So fancy. So how many possible flush hands? Well, we've got one for each suit. We found for the one suit for hearts, it can be any suit, right? The 13 can be for any suit. And so what we have is we have 4 times 13, choose 5, which is 4 times 1287, putting me at 5,148. Just as a little side note here, this is the number of suits, and this is number of flushes in each suit. What if we want to know how many ways can a full house of 3 10s and 2 queens be drawn? Okay, I'll write it down while you think about it. How many ways can a full house of 3 10s and 2 queens be drawn? So if we start by thinking about it, okay, so I need 3 10s and 2 queens. So the 10s, there are 4 10s, right, and 4 queens that I can choose from. So I can deal with the 10s, right, and have my 3 10s, and I can figure out how many combinations of the 3 10s I have. But then for each of the combination of the queens, right, that's going to be replicated. So I'm going to be multiplying these options just like we did up here, right? Here we just had 4 as the number of suits. But now if you think of it as, okay, I can have the number of combinations of the 10s times the number of combinations of the queens, right? So a lot of the time we're just kind of multiplying stuff together. So we've got 4 choose 2. Actually, the way I said it was 4 choose 3. The 10s first, right? Because I'm choosing 3 10s. Times 4 choose 2. And these are the queens. Four choose 3 on your calculator is just 4. And 4 choose 2 is 6. Obviously, those are small enough to just kind of flesh it out with the formula, but we can just use our calculator, so why not? So of course that puts me at 24. If you think about it this way, just because I know that arriving at this multiplication is a little bit tricky, right? And so if you think about, okay, well, I can figure out how many different combinations of 10s I can get, right? Turns out it's only 4, so that's manageable, right? But for each of these four, the queen, the set of two queens were being held steady, right? And then we can change the set of queens, and there's 6 different ways that we can have 2 queens. And that's why we multiply. Pascal's triangle, is that ringing a bell? No. I wanted to mention it here. Lizard from Tangled. So, oh, probably not. No, that sounds like, yeah, some guy playing a triangle. That's pretty fun too. But so Pascal's triangle is really just kind of a poor man's calculator. It's a way of figuring out the choose functions. I remember in my computer science course, like way back, first year computer science, I was terrible at it. But we had to program Pascal's triangle up to a certain, I don't know, certain line. It was really hard. So that's why I want to introduce you to what it is, at least. Well, you can think about it. Like I said, it's kind of a poor man's calculator. So back when we didn't have this fancy choose function that could just do a combination of whatever we wanted, essentially, within some sort of numerical reason, people would just have Pascal's triangle printed out, and you can just find combinations. But so we're not going to use it, but it's good to know that it exists, and that's why it exists. So Pascal's triangle looks like this. So it has a 1 up at the top, and then it's going to cascade down. And on either side, there's going to be 1s running along the edges on both sides. So we've got 1, 1, 1. Okay. So far, so good, right? Then 1, 2 in the middle, 1. Okay. What's fun about it is that the number in the middle is going to be the sum of the 2 above. Okay. Sum of 2 numbers above. Okay. And always having a 1 along the edges. So 1, and then 1 plus 2 is 3. 2 plus 1 is 3. 1. Okay. We'll go 1 more. 1, 4, 6, 4, 1. And then just kind of keeps going and going and going. Okay. So I'll do that with a little dot, dot, dot. Okay. So this is Pascal's triangle. Not that useful for the top values, but definitely once you get down to you know, the 10th row or the 14th row, gets really big. And so what we have here is, let's see here. We can rewrite Pascal's triangle with combinations and choose R, where N is the row and R is the diagonal row. So I'll draw them up above here, but first I'll write it out. Where N is the row and R is the diagonal. Okay. So here, we start at n equals 0. So that's this row here. N equals 1, n equals 2, n equals 3, n equals 4. And then this first diagonal, r equals 0. So we start at 0, now 1, right? Because we've got that 1. So 0, choose 0 is just, there's only one way to choose 0 things out of 0. R equals 1, R equals 2, R equals 3. Okay. So we get these kind of diagonal rows. So what we can do is we can say, okay, well, 3 choose 2, 3 choose 2 should be 3, right? Let's try it out on our calculator. 3 choose 2 is 3. Good. How about, let's make sure we get 6. So that's going to be 4 choose 2. Right? So 4 choose 2 gives me 6. Yeah. So what this looks like is we can rewrite it as 0 choose 0 equals 1. 1 choose 0 is 1. 1 choose 1 is 1. 2 choose 0 is 1. There's always only one way of choosing 0 things, as well as there's always only one way of choosing all the things. So 2 choose 1 is 2, and 2 choose 2 is 1. 3 choose 0 is 1. 3 choose 1 is 3. 3 choose 2 is 3. And 3 choose 3 is 1. We'll just do one more row here, because otherwise I'm running out of room. 4 choose 0 is 1. 4 choose 1 is 4. 4 choose 2 is 6. 4 choose 3 is 4, and 4 choose 4 is 1. Oh. Okay. So what I will say is this is just something that's good to keep in mind, right? If you have Pascal's triangle, then you can just use it to find your combinations. But like I said, we'll just use our calculator, just like I use the calculator to just check things in here, right? So it's just a little good to know tidbit, okay? And it's good to know what Pascal's triangle is and what it's all about. So we can use Pascal's triangle to find combinations but we will just use our calculator. We'll just use the NCR function on our calculator. So kind of a fun thing to play around with. Okay. So that's the end of 12.2. We're going to move into 12.3, but like I said, 12.3 is just, you know, different scenarios. How do we distinguish between needing permutations or combinations, or maybe both or neither? Right? Basically just a bunch of examples. So 12.3 is called counting without counting. Right? We're no longer going 1, 2, 3, 4, 5, 6, but we are counting large numbers of things. So 12.3, counting without counting. Okay. Start with an example. Classify as a permutation, combination, or neither problem. So we're not going to go through and do it, but let's just get used to reading these problems and figuring out what we would need to do. Right? So A, the number of 3-letter words, right? So just combinations. The number of 3-letter words so I'll put words in quotes from the set MATH. I'll keep writing these out while you think about it. The number of ways you can arrange, or you can change a $1 bill with 5 nickels, 12 dimes, and 6 quarters. Just leave some space here. The number of ways you can change a $1 bill with 5 nickels, 12 dimes, 6 quarters. The number of ways a 5-card hand can be drawn from a deck of cards. Helps that we just did that. B, the number of different 5 numeral combinations on a combination lock. Number of different 5 numeral combinations a combination lock. The number of license plates possible with 3 numerals followed by 3 letters. So, because I'm cutting it close on time here, how about we'll just go through and talk through each of these. So if we want the number of 3-letter words, right, then we just don't want the set of MATH, and the order doesn't matter. If we're looking for distinct words, right, then we're looking at a permutation, right? So it's a permutation for distinct words. For the next one, right, we're always checking, okay, is there repetition allowed? Okay, if there isn't, then it's either a permutation or a combination. If there is repetition allowed, then it's going to be neither, right? And so the number of ways that you can change a $1 bill with 5 nickels, 12 dimes, and 6 quarters, we're not solving this problem, but we need to check in and say, okay, well, does the order matter, right? Does it matter if I have 5 nickels and 1 dime, right? Or is 1 dime the same as 5 nickels? Or 1 dime, 5 nickels the same as 5 nickels, 1 dime? Right? Order doesn't matter. It's the same as the hand of cards, right? The order that I get these things in, it's just going to make up a set, and it's going to have some total value. And as long as that total value is $1, then you're safe, right? And so this is a combination since 2 quarters and 5 dimes is the same as 5 dimes and 2 quarters. Trying to squeeze it in there. So the order doesn't matter. Same thing with the deck of cards. So a 5-card hand, this one we just did, right? So the order doesn't matter. So it's a combination. The number of different 5 numeral combinations on a combination lock, I'm having a hard time with this one because the permutations, we would be replacing the numbers. So the textbook says it's a permutation, and fine, because of course the order matters. If I tell you, okay, the code to get in is 1, 2, 3, 4, 5, that's going to be a different code than 5, 4, 3, 2, 1, for example, right? And so if the order matters, then it's a permutation. It doesn't specify that they have to be unique numbers, so that's my hang up. But in terms of, is it a permutation or a combination? It's a permutation because the order matters. And then for the last one, the number of license plates possible with 3 numerals followed by 3 letters. Again, there's, we can use multiple, we can use the same letter multiple times, right? But kind of, so both of the combinations, permutations are out, right? But we could still figure out how many we have, right? And so it's a combination of, no, it's neither. I was gonna say it's a combination of permutations. It's neither, because we've got this repetition. So it's neither, since the same letter can be used 3 times, right? So there's repetition. So I'm out of time. So what I'm gonna do for next day is I'm just gonna quickly type up these examples, and then we'll just work through them kind of briefly on Monday, or yeah, on, yikes, I don't see you guys till Monday. That's right. So if there's repetition, it's not a combination or a permutation. Yeah, so what I'll do is I'll just quickly type up these examples, and then we'll have them, and then we can just kind of work through them. Cool. All right. Any questions? No? All right. Then I'll see you on Monday. Bye, guys.